Hi everybody, I hope you guys are doing great. In the last video, we have discussed about what an electric dipole is. We have seen that electric dipole is a very unique charge distribution, and it is very important for us to understand the behavior of dipoles because many of the molecules available are present in the form of dipoles. So molecular modeling becomes that much easier if one understands the behavior of electric dipoles. In the last class, we also calculated what will be the electric dipole of a particular point P which is lying on the axis of a dipole. Now in this video, what we shall do is we will calculate the electric field. We will calculate the electric field at a point P lying perpendicular to the center of the axis. We can call this as equatorial point, or we can say that any point P which is lying on the perpendicular bisector to the axis of a dipole. So let's map this situation. So we will first take a positive charge, and then we will consider a negative charge. So these two charges are separated at a distance d. So these two charges constitute a dipole. Now we would like to know what is the electric field at this point P, which is lying exactly on the perpendicular bisector, anywhere on the perpendicular bisector. So this is the situation. So we need to calculate what is the electric field at the point P. Now let's map this situation better. Sorry. So we will draw two lines. So this line connects P with positive charge. This line connects P with a negative charge. Fine. Now let's say that the distance between this point P and the positive charge is R. Let us assume that the same distance R separates the point P and the negative charge. Now let's try to map the electric field lines. So let's choose another color. Now this is the positive charge, so this is going away. The electric field line is protruding away from the positive charge, so this is going to be E plus. On the other hand, the electric field lines will be going towards the negative charge, so this is E minus. So where will be the net electric field? The net electric field will be somewhere here. So let's extend this line. So this will be the direction of the net electric field. So this is E net. Now let's first try to calculate the magnitude of the respective electric fields. So let's go back to the conventional color. So E plus will be equal to KQ over R square. This is elementary. That's the value of the electric field magnitude. So what's going to be E minus? E minus is also going to be KQ over R square. Sorry. So both are going to be one and the same. So it's fair to say that E plus is equal to E minus is equal to E. So we can call this as E. So this can be called as E, and this also can be called as E. Now we need to calculate what is the net electric field. So how do we calculate the net electric field? Now, a very simple way of calculating net electric field would be to resolve this in terms of horizontal as well as vertical components. So these two angles are theta. So let's redraw the situation here for more clarity. So this is the straight line. So you have this point P. This is one vector which is E. This is another vector which is also E. Now this is theta and this is theta. Now if you want to resolve this vector, this particular vector, into horizontal and vertical component, so let's take another pen. So this is going to be the horizontal component, and that's going to be E cos theta. This one. Similarly, if you want to resolve this in terms of vertical component, this is going to be it, and this will be E sin theta. Similarly, for this vector, if you want to resolve this vector into vertical and horizontal component, the horizontal component once again is going to be E cos theta. The vertical component is going to be E sin theta. We can easily see and understand that this E sin theta, sin theta and this E sin theta are directed opposite to each other, meaning they are going to eat up each other. So they are going to get cancelled. Okay. So we are going to have a situation where the E cos theta prevails. So the net electric field, that's what we are looking at. So let me write it down here. E net is going to be 2E cos theta, because we have 2 cos theta here, E cos theta, which is because of this vector, and another E cos theta, which is because of this particular vector. So we have now 2E cos theta. Now you can substitute the respective values. So this is going to be K Q over R square. That is very simple. Now we need to find this cos theta alone. So cos theta is, you can say that this angle is also theta. So cos theta is adjacent side divided by hypotenuse. So here the adjacent side is d over 2, because this is d, this entire distance. So this distance has got to be d over 2, and this is r. So you have d by 2r. So this 2 in the downstairs and the 2 on the upstairs will be cancelled. So the net electric field will be E net is equal to K Q D over R cube. But there is a catch. We know already from the previous lecture or video, this QD is nothing but the electric dipole moment vector, which is P. So substituting the term for P for QD, you get KP over R cube. So if you want to write in terms of vectors, of course we can do it. So let's write it here. So E net, so this is a vector, is K P, this is a vector, and R cube. Now the directions are such that the electric dipole moment is always along this direction, from positive to negative, from negative to positive. But the net electric field is running along this particular direction. So here the net electric field and the net dipole moment are oppositely directed, so it's always customary to put a negative symbol here. So this is the value of the net electric field of a dipole in connection with a point lying on the perpendicular bisector of an axis. So you can see that the value of the electric dipole strictly depends on the orientation. We saw that along the axis the value of the electric dipole is 2 kp over r cube, but at the equatorial point it is kp by kp over r cube. But one thing what is very common is the net electric field is always inversely proportional to 1 over r cube, unlike a point charge where the net electric field is inversely proportional to 1 over r square. So this is all about dipoles. We shall see more concepts in the next class. Thank you.